Okay, everybody, welcome to this session on Program Analysis 2. And I'm very happy to welcome you all to this session and to let you know that we have 6 speakers today presenting 6 different papers. The first 2 papers are Journal First papers. Then we have a New Ideas and Emerging Results paper. And then we have 3 papers from the technical track. Each of the presenters will give us a very quick overview of their research. So as you know, if you want to learn more about it, you can go and click on the recordings and see a longer presentation. But each of the presenters will give a 5-minute presentation. And we're going to do all 5 of the presentations first. And then after that, we have half an hour for a discussion. So there's some different ways that you can kind of line things up for discussion. Obviously, during the discussion, you can, raise your hand by putting something into the messages, and then you'll have a chance to ask your question. But if you want to create a kind of placeholder for a question as you think about it, please feel free to just type questions into the message board on the right-hand side. And then make sure when you type a question in, though, you say who it is for. So just remember the presenters' names or the something about the paper. So if you ask questions during the first half hour, we're going to line them up and then we'll come back and cycle around to them. So I think to make this a great interactive discussion, I think it'd be really good to do that. So without further ado, our first, whoops, okay, that's obviously not going to work. I guess I ran out of my own time there, and I was testing the timer. So our first speaker today is going to be Fuchen Ma. Fuchen is from Tsinghua University. And Fuchen, do you want to go ahead and share your screen?
Yes, thank you. And I'm sharing my screen then.
Great.
Okay, can you see my screen?
Yes.
Okay, so I'll begin. It's grateful to be the first speaker in this session. And my name is Fu Chenma from Tsinghua University, and my research focuses on blockchain security. And today I'm going to introduce you a tool named Pluto to expose vulnerabilities in intercontract scenarios. And this is a joint work with University of Waterloo and WeBank. Intercontract vulnerabilities refer to the bugs hidden in smart contracts, intercontract calls. And here is an example of the intercontract vulnerability. In the first contract named rule contract, it defines the threshold calculation rules of an investment. And the threshold depends on the target year of the investment. And in the other contract named investor contract, it's used to invest tokens to each target. And if the investment amount is more than 300,000, 1% of the threshold value will be deducted as the handling charge. And the investor contract has an overflow vulnerability. If a malicious investor inputs a large value of the investor token, there will be an overflow in the add operation. We tested this example with several state-of-the-art works, including symbolic execution tools like Allinit and Mathreal, and as analysis tools like SmartCheck and Securify. And as Table 1 shows, all the tools fail to report the vulnerability. Besides, both symbolic execution tools report another add operation in that example as a vulnerability, which is actually a false alarm. And generally, the existing tools fall in intercontract scenarios for two reasons. And the first is they fail to collect semantic information from the intercontract logic. And the second is they fail to check the path reachability correctly. And this shows how the tools like OINIT acts like this in this example when processing this contract. First, it executes the opcode named execution code size. And then if the called code exists, ORINT executes the call opcode. And if the execution succeeds, ORINT will load the results from the memory and return the data. When processing with the call opcode, ORINT first pops 7 elements from the stack and then pushes back 1 to the stack, which indicates that the call is successful. However, when the opcode mload tries to load the return data from the memory, it gets a signature of the called function, which is a very big number. And in our case, this huge number has been assigned to the variable named threshold. Consequently, the first condition of the if branch in that example cannot be satisfied, and the else branch will then be executed. And this leads to the false negative as well as the false positive by the ORINT tool. And this picture shows the overall architecture of our tool named Pluto. And the inputs of the system are the target contract as well as the code contracts. And the outputs are bug reports and some advice for developers on those vulnerabilities. And there are 3 steps in Pluto: the SFG construction, the SCPC detection, and bug validation. And with these steps, Pluto can successfully support the bug detection in inter-contract scenarios. Pluto detects inter-contract vulnerabilities by constructing an inter-contract CFG. And to do that, first it constructs an inner contract CFG. Then it splits the blocks with call opcode. And finally, it links the blocks with return opcode. And after that, Pluto collects inter-contract path constraints. It first collects the inner contract constraints, then it analyzes the call relation and calculated the inter-contract variables constraints them. Here is our evaluation results. The evaluation is first conducted on 150 manually constructed contracts. And the result shows that Pluto can detect 80% of the injected inter-contract vulnerabilities. The bugs that Pluto failed to detect is due to the unreachable address of the call-lead contract. As for the Solidify data site as shown in Table 3, and Pluto reported 681 valid vulnerabilities on 100 contracts, which is the best of all the other tools. We then evaluated Pluto and the other 4 tools on 8,173 real-world solidity fails with 39,443 smart contracts. And the result shows that Pluto can find most vulnerabilities in real-world contracts, and it can detect 36 inter-contract bugs, while ORINT and Mesrio can only find 12 and 16, respectively. And that's all. Thank you. For more details, please refer to our paper published in HBTSE. Thank you for your listening.
Great. Thank you very much, Fujin. Okay, so yeah, I think I saw somebody applauding. So if you want to find out where to kind of let's see, down at the bottom, if you want to join in, you can click on that smiley face and you can kind of give some real live interaction after each talk. Okay, so that was a great talk to start us with. The next talk is going to be by Ryan Williams from Northeastern University. And Ryan, you can introduce your talk yourself.
Great, thank you. Screen here. There it goes. All right, everyone can see that, right? Cool. All right, so I'm Ryan Williams, and I think Tongwei Ren from WPI is here as well. We worked together on this journal-first paper for guided feature identification and removal for resource-constrained firmware. So first off, protocol software, like most programs are, they tend to be very bloated. So when we were looking at things that ran on IoT and embedded systems, it was pretty paramount that we were able to minimize the amount of space allocated for the binaries that would be deployed. And for our targets for evaluation here, we saw that the leftover code that would relate to what we deemed a quote unquote feature, that could account for up to 29% of the overall lines of code that went into the final compiled binary. So one of the one of the projects that we looked at was a different implementation of a MQTT protocol. And MQTT is a pretty simple publisher-subscriber framework like this, where you can have a set of publishers or data producers, like temperature sensors, which subscribe to a given topic, like temp in this case, and they will periodically publish their readings to the MQTT broker. And then on the consumer side of that, we have the devices that act as subscribers to the given topic, and they listen for the readings from those individual sensors. So we can imagine in a case like this, MQTT, we saw that this came bundled with 19 discrete features. But if we're dealing with a simple use case like this, we could imagine not necessarily needing every specific feature like TLS and WebSockets if it's something that doesn't have like a user interface front end, for instance. So to that end, we designed PRAT, Program Representation Analysis Toolkit. And the way this works is we have it split into 3 different stages. So the first requirement is to provide the project's source code. And once you pass that to the analysis step of PRAT, it infers these features via an analysis of the build files like make, CMake, AutoConf. And once it gets a list of those unique features, we then go through the process of compiling the binary with that feature enabled and with it disabled. And this is done via the native build system. So like passing a flag via make, for instance. And then once we have each of these compiled binaries, we have them instrumented to capture the code coverage. And we run a bunch of unit tests, end-to-end tests, and try to generate as much coverage as possible. And then we posit that a given code block that was executed in one of those binaries but not the other, that will pertain to the feature that we were actually toggling. So once we have this mapping of features to the actual code artifacts, we pass that to the step that involves a human in the loop, where the analyst is presented with all this information in a web interface, and they can select and many features that they want to actually disable from the code base, and they'll see how many lines of code they will effectively be removing from the compiled binary, as well as where they fall within the code base. And the next step is back to the automatic part where we have the feature removal. They just delete all the code in line, recompile, run all the tests. Once we're happy that everything looks copacetic, we then say it's ready for deployment. So the main part of our evaluation looked at these 3 big topics. One was, can PRAT identify all the features within a code base? Does our approach actually lead to a measurable reduction in the unused code? And lastly, do the deep loaded programs that we compile retain their correctness after feature removal? So for feature identification, for all of our 5 evaluation targets, we found all the true features with 1 false positive. The false positive here was for a case where it was a flag for building with or without a shared library. So that didn't actually pertain to what we defined as a feature, but the system inferred that as a feature. Just heuristically, it seemed to match. It doesn't cause any breakage, but it does just give you 1 extra feature that would return 0 lines of code to remove. For our overall code reduction, we see here manual is the manual toggling of a feature to remove it from the code base. And then we have the PRAT reduction. We can see in most cases there is a non-trivial to a significant reduction in code via PRAT's approach. And lastly, for the correctness after feature removal, we reran all the same unit tests that we had for the initial analysis step, but in cases where those weren't sufficient, we used the CLI symbolic execution environment to generate new test cases. And for those, our CLI generated tests actually resulted in, on average, 80.2% code coverage. So that gave us some confidence in saying that we didn't effectively break or introduce new bugs to the binary. All right, so yeah, that's PRAT. We basically introduced a kind of novel approach for identifying and removing code and software that pertains to these features, where the features are automatically inferred from the build system, and they're presented in an easy-to-use UI for aiding analysts in the feature removal process. Couple limitations to put out is if the code base is very large and you have to compile it n many times to find the feature to code mappings, that can be a little difficult as the compilation time can be non-trivial. And the precision of the code removal is very much reliant on the coverage quality of tests. So if we have tests that only get 50% coverage, then we're not going to be removing as much or the optimal amount of code that we could be removing. Okay, and that's it. If there's any specific questions, feel free to reach out to me directly or see the full presentation and paper on the conference website. Thanks.
Okay, great. Thank you very much, Ryan. And we're going to move on to our third speaker, who is Thanh Dat Nguyen. And Thanh Dat is from the University of Melbourne.
Yes, so perhaps I should start sharing my screen.
Yes, please.
Okay, so I hope everyone will be able to see it. Okay, so hello, I'm Thanh from the University of Melbourne, and our research program is the University of Melbourne, George Mason University, and University of Technology. And this is a quick presentation.
I think we're having a bit of a problem with the audio. Are others having a hard time hearing it too?
Oh.
Yes.
Okay, so
That sounds better, I think.
is this better now?
Yes.
Yeah, that's better.
Okay. Yeah,
Perfect.
and this is the representation for the work towards the analysis of graph neural network. Okay, so our work is about the analysis of graph neural network. So maybe the first question we should ask is, why should we do this? And our answer is that the JNN is useful toward targeting a great of very interesting problem. For example, since it's able to take input as the graph, it is useful in knowledge graph reasoning, molecular structure reasoning, and scene graph reasoning in autonomous driving, and social network graph reasoning. However, just like any other type of deep neural network, the JNN is also has the problem of being a black box. And with recent work shows that the JNN is prone to be attacked. I believe that it is necessary for us to start formal analyzing the JNN. So while the formal analysis has been done in feedforward neural network, the conversion to the graph neural network is not as easy because of the major differences between the feedforward neural network and graph neural network. This difference here is why the feedforward neural network takes input as a single vector. The graph neural network takes input as a graph, where each node and edge can be associated with the feature vector itself. This leads to two major challenges. The first is dynamic computation, since the number of nodes and edge in the graph can be arbitrarily large. This leads to an arbitrary number of features. And the second, even when we have a fixed structure, then we can convert the JNN into the corresponding feedforward neural network, but it would still be about the number of edge times larger than the normal feedforward neural network. So this is where the JNN infer came in. So the JNN infer key contribution lies in 2 points. The first is that it elaborates the set of most frequent influential structure. In brief, these structures are the set of node and edge that contribute significantly towards the prediction of the graph neural network. And thus, they have two useful properties. The first is that their computation would approximate the computation of the full graph neural network, while their structure are fixed and small. This helps us address the formation challenge of dynamic computation and scale. The second contribution is that we introduce a new mechanism to unroll the JNN computation on each of these formation substructure into an equivalent feedforward neural network. this would allow the JNN infer to leverage existing feedforward neural network analysis tool to analyze the JNN property on each of these substructures. And finally, we also find the required predicate for this property to statistically hold in the full graph. In the end, the JNN infer would output a property in terms of like the precondition on the input, implying the postcondition on the output. So that's it. Thank you.
Okay, thank you very much, Sandat. Okay, so our next speaker is Peiming Liu, and Peiming is from Texas A&M.
Yeah, can everyone see my screen?
Yes.
Okay. First, thank you all for attending. And today I will introduce my work on PUS, which is a faster solving algorithm for inclusion-based point analysis. So for those who might not be really familiar with the topic, point analysis is actually a fundamental technique used in enormous amount of static analyzers. On one hand, you won't have a precise point analysis because it dramatically enumerates reported by the analyzer. On the other hand, a precise point analysis is also infamous for its poor scalability. So at a high level, point analysis computes a set of objects that could be pointed by a pointer during runtime, which is often referred as the point to set. And it helps to language pointer. It also helps to resolve indirect function calls such as function pointers and virtual functions in C++ and Java. And as its name suggests, inclusion-based point analysis computes the pointer information by abstracting different statements into inclusive functions, as shown in this table. And then the problem can be abstracted into with each node representing a pointer or variables, and each edge representing inclusive functions. The result is then computed by finding the minimal fixed point such that all the functions are satisfied. So there are currently two state-of-the-art solving algorithms we use to compare with our method. At a high level, a wave propagation algorithm will first topologically sort the entire graph and then propagates the point to information in a topological order and repeat it until reaching fixed point. And the deep propagation algorithm propagates the point to information in a depth search manner. And the problem with these two approaches is that both algorithms actually take the function graph as a whole, and they have to process the entire graph at each iteration. But what we observe is that at each iteration in the solving process, actually only a very small amount of subset of the graph actually affected by the update from the previous iteration and are required to be processed in this iteration. So the pointer information only need to be propagated on a small effective subgraph instead of the entire function graph in each iteration. So take this as an example. When compared to wave propagation, partial update solver will only process node 2, 5, and 8, as they are the only node that are affected by the update from the previous iteration, while the wave propagation have to retopologically sort the entire graph. And when compared to deep propagation, PUS avoid redundant computation because it propagates the pointer information in an optimal order on the small subgraph, and deep propagation will have to process the information from V1 to Vn twice. So of course, this is just a very high level introduction of the algorithm, but I think this should capture the essence of the algorithm. And also we formally prove the correctness of the algorithm. If you want to know more, please refer to our paper. And finally, we evaluate our algorithm on a large set of benchmarks. This table shows that during the whole solving process, the effective subgraph only contains about 3% of node and 2% of edges of the entire graph on average. So which means that actually the most of the redundant computation can be skipped. And for performance, when applying partial update solver on context insensitive, field sensitive point analysis, it is more than actually 3 times faster than wave propagation and more than 2 times faster than deep propagation. And when applying on solving context sensitive point analysis, PUS is actually more than 7 times faster than the wave propagation and about 9 times faster than deep propagation on average. And I think that will be all my presentation. Thank you.
Okay, great. Thank you, Peiming. Okay, so now for our fourth presentation, we have Hyun-Soo Kim from KAIST in South Korea.
Hi, can you see my screen?
Yes.
Okay, so Hyun-Soo Kim from KAIST, and in this talk, I'm going to present about learning probabilistic models for static analysis alarms. This is a joint work with Mukund Raghuvathaman from University of Southern California and my advisor, Kyung-ho. So in static analysis, one of the big challenges is false alarms. So since the alarm report provides a bunch of false and true alarms with no order of significance, a developer has to look into each alarm without any guidance. So the alarm ranking system was introduced to improve such usability and effectiveness of static analysis. The system initially gives a ranking of the alarms sorted by the likelihood of being a bug. The developer inspects the alarm from the highest ranked alarms and give a feedback to the system. The feedback is whether the alarm was true or not. Then the system integrates the feedback to provide better alarm rankings to the users. This is a typical form of the Bayesian inference that is updating the belief with new information. So by the update, the system would recalculate the probability of the alarms and provide it to the user. And this iteration goes along. And ideally, the system should push the ranking of true alarms upward within less user interactions. And here's the result with wget, the well-known GNU utility. And with sound interval analysis to detect buffer overflows, we get hundreds of alarms while only 6 of them are bug. And you may imagine how inefficient it is to go over the entire alarms for just a few bugs. And the graph on the right shows how the true alarm rankings change as the user interactions with the system. The faster the ranking drops to 1, the better the system is. An orange dashed line shows the performance of the system, requiring less than 200 rounds of interactions until finding all the bugs. But still, as marked with black arrows, the system shows awkward moments where the true alarm ranking suddenly spikes up. If it could have resolved the moments, we would significantly enhance the performance. And that being said, the blue line denotes the performance of our suggested learning framework. The learn model reduces the alarm inspection burden by about half amount additional to the original system. The problem of the original system is a sudden drop in probability of the true alarm. From the given program, we construct a Bayesian network as shown on the left. The network captures the data flow within the program, and one may focus on the alarms at the bottom. Blue alarm 8 is a false alarm, and alarm 11 is a true one. Two alarms are tightly coupled, just a few nodes far away. Now the problem happens when the feedback of false alarm that is tightly coupled with the true alarm is given to the system. This corresponds to the sudden increase in true alarm rankings that we have just described. And we call it false generalization problem. Literally, the problem is due to falsely generalizing the feedback from the user to suppress true alarm ranking. So in the Bayesian network, we can compute the probability of nodes or random variables. And note that initially, the true alarm 11 was marked with high probability, 0.89. But when the user says the alarm 8 is false, the system integrates the feedback to recompute the probability of alarms. The computation is nothing but conditional inference over the Bayesian network. And basically, the system propagates the blame of misinforming the false alarm to the other facts in the graph. The yellow nodes describe the blame propagating from the false alarm to the true alarm. And the blame causes a drop in probability of the node. If you see the bottom right of the figure, as the feedback is given, the probability of the true alarm drops from 0.91 to 0.4. So to mediate the problem, we focused on syntactic information to improve the expressiveness of the probabilistic model in addition to the data flow of the program. It can also be easily generalized over programs. For example, here we observe that there was a loop involved in line 7 of the program, then added to the network. As a result, it effectively mitigates the severe drop in likelihood of the true alarm. We can systematically automate the process of adding syntactic information according to the syntax of the programming language. So this becomes the basic idea of our learning framework. And here's the result for the experiments. For evaluation, we count the number of user interactions with the system until finding all the bugs per analysis. Note that the baseline model called Bingo, marked in blue bars, already reduces the number of alarms to be inspected by large amounts. Then, in addition to that, the performance of our learning framework are indicated as red bars. With the learned models, we additionally improved by 33% for interval analysis and 22% for taint analysis. So if you're interested, we highly recommend reading our paper or even watching the video for the extended version. And the extended talk further describes the following details. And thank you for listening.
Great, thank you very much, Hyun-Soo. Okay, and our sixth and final talk before we go into our open discussion is presented by Akshay from UCLA, University of California, Los Angeles. You seem to be muted, Akshay. Your showing is muted.
Oh, yeah.
Yep.
Is it better now?
Yep,
Okay. Good. Okay. So hi, my name is Akshay, and I'm going to be presenting our paper, Fast and Precise Application Code Analysis Using a Partial Library. So analysis time is still an issue for cases like really large programs or a large collection of programs like an app store. And an application code analysis is one technique to offer a speed up by focusing the analysis on just the application code. So if you see the program code split up over here in our NJR benchmarks, we have the application code taking up less than 1% of the actual 1% of the whole program, whereas the library, which includes the standard library and third-party libraries, constitute a majority of the program. But if we take the naive approach of ignoring the library entirely, we miss too many errors. Right. So to actually evaluate how an application code analysis does, we define two metrics. And for this, we're going to use the whole program analysis results as the ground truth. So the first term is precision, which is defined as out of all the application code analysis errors, how many were true positives? And the second is recall, which is out of the whole program analysis errors, how many did the application code analysis catch? So the current best application code analysis tool for Java is Avros, and here is an oversimplified view of how it works. So the whole library is over-approximated into a really compact summary, and we have a single summary pointer that merges information from the whole library. So the result with the whole program analysis as the ground truth is that the speed up is very large because this summary is really small compared to the size of the library. And recall is theoretically 100% because we've done an over approximation, but precision is really poor. It's only at 59% because too much information gets merged into the summary pointer. But let's look at what user expectations on precision are. So several user studies have concluded that static analysis tools should aim for close to 80% user perceived precision. But the issue is that whole program analyses themselves struggle to achieve 80% user perceived precision. So what we need from an application code analysis is 100% precision relative to the whole program analysis. Because if we don't get this, we're definitely going to fall short of user expectations. But the current best available is Avros, which only gets 59% precision relative to the whole program analysis. And the reason Avros is designed this way is that it's designed as a recall-focused verification tool. So what can we do to address this gap between what's available and the 100% precision that we want? And for that, we introduce a new tool, QueryMax, which acts as a pre-processor for an existing static analysis tool. So QueryMax takes in the specification of the application code, library, and analysis queries. So here, the analysis queries, say for cast check analysis, would be all the downcast instructions in the program. So taking these three inputs, QueryMax selects a partial library that covers most of the client analysis queries. And library pointers outside the partial library are treated as the bottom element in the abstract domain. So for example, in a null pointer analysis, everything outside the partial library would be considered as not null. So the partial library is basically an under approximation of the actual library. So using the partial library and the application code, the existing static analysis gives us errors which have 100% precision, 87% recall, and 10x speed up. So we've traded off some amount of recall for a really large speed up. And that's about it, the presentation. Thank you for listening.
Okay, great. Thank you very much. Okay, so thanks to all of the presenters for giving us really nice, succinct overviews of their work. We do actually have some questions already lined up, so we'll just go through them. So I think the first question is by Peiming for Futan. Peiming, you want to ask your question?
The question is, I saw the presentation and the root cause of the vulnerability in your presentation is actually an integer overflow, right? And apart from the integer overflow, what other types of bugs does your tool detect?
Sorry, can you repeat that question? I'm not so clear here.
Yeah, because when I see your presentation, your presentation, the vulnerability of the example vulnerability.
Yeah.
The cause of that vulnerability is due to an integer overflow, right? But apart from that, because basically you try to see what the intercontract whether it can trigger integer overflow, something like that. But what other types of bugs does your tool detect?
Okay, thank you for your question. And for now, our tool support 3 types of vulnerability detection. It contains the overflow and the underflow, integer overflow and underflow, and time step dependency and reentrancy. And we think we can add more types for the detection in the future. That's our future work, and it depends on how we define the checkers, and for the symbolic execution part is basically the same. So I think in the intercontract scenarios, we will add more checkers, more oracles to support more types of vulnerabilities detection, and we will try to support more tabs in the future.
Okay.
Okay, great. Thank you. I'm basically going to just kind of work through the questions in the chat and then open for anyone else that has questions. So the next one is from Akshay, who has a question for Peiming. You're muted still.
Hello.
though.
Yeah,
Yeah.
Peiming.
Okay.
So in your paper, you actually just mentioned two possible, the two existing works, which were either iteratively solving everything or doing it in the
depth search. Yeah.
Yes. So actually, there's another. There's another paper I remember from back in 2003. I'll just post the link, which actually had this concept of a work list, and the idea was that that if there's a node which has some of its has propagated, you put all its edges into the work list and you only sort of solve the constraints for stuff that's in the work list. So actually my question is pretty much similar to last question on the chat, and I agree that tools like Dupe and Suit in Java do this.
Yeah,
I'm not that aware of C++.
Yeah, I think that's a good question, but I'm not sure about the paper you just mentioned. And actually, for work list, actually every point analysis internally has a work list, and the work of mine is how to reduce the size of work list and how to arrange the sequence of the work list in an optimal order such that you can, because eventually you have to reach a minimum fixed point, and how you can reach that fixed point quicker. So even the tool that I introduced actually has a work list in its implementation. And another thing is, I do know there are some other solving algorithms, but actually with similar performance. The reason why I picked this two is because I found the most recent paper are still using these two algorithms. At least the aim for C and C++, of course, are using these two algorithms, and that's why I use that to evaluate our method. And this math and the two compared method, according to my own research, I found them have the one, maybe probably the most competitive performance compared to other existing tools. So maybe I missed some papers. Maybe I can check what you mentioned. And I think I can also start to answer the second question, because I think these two questions are actually pretty similar. The Dupe questions.
So
let me, Francois, do you want to add anything before he tries to answer your question, or do you want to say anything?
Yeah, it's very similar. So there's as actually already pointed out, there's a complete history of publication, mostly on starting with Deck and Eric Bottom and so on and so forth. So yeah, pretty much the same question. I don't think people are doing points to analysis by scanning the whole graph on every single pass until
I think the first data, what you mentioned, I think the data log method you mentioned, that definitely a very interesting line of research, and I really admire their works. And I think, but in my opinion, I also argue this in my paper, I think these two actually represent two different lines. One thing is, I mean, the data log, you can represent the constraints in a mathematical ways. You can extract those constraints, and you can rely on data log to solve those constraints. And on the other hand, many times people want to have their customized solvers, and that's also many existing analyzers are still building their own, writing their own solving algorithm instead of relying on Dupe to solve their point analysis constraints. And when you are looking at those kind of work, they are still using maybe similar algorithm as I introduced in my paper. And that's one part of my answer, because I think these two may represent different ways. And if you want to build a customized solver, you can easily tweak it and adding some heuristic that cannot be easily expressed in data log. Another reason why I did not compare data log performancely with our work is that it's very hard to really get insight of which one performs better, because it's hard to control all other variables, or a different kind of, like how you model field sensitivity, how you model different things, how you can make sure these two algorithms compute exactly the same result. And also, I'm not an expert of Dupe, of course, but I know that they're not only partially solve the graph, they're also doing it parallelly, which is not discussed in the paper, but it has been proved that this is actually very easy to do for program like point analysis. I think maybe 2 years Popol paper, there are some papers that prove how you can easily do parallelization to solve these constraints, but it's not discussed, and I did not implement in my prototype. So that's also another reason why I did not compare directly to Dupe in my paper. And I think these two aspects should answer my question.
Okay.
Answer your question?
Yeah, okay. I think we're going to thank you. That was a great answer. I think we're going to move on, because I want to make sure that everybody gets at least one question. So I think we'll have Akshay's question for Hyunsu, because Hyunsu hasn't had a question yet. So Akshay.
Yeah, the question was in your results, for example, for the buffer overflow analysis, I was wondering if the analysis is too imprecise because, like, say one of your benchmarks, CFlow, had 805 alarms, but just one true positive. So is there something I'm missing, or are there other true positives that you don't have ground truth labels for?
No. So I think it's the point of view how you see the precise or imprecise. So to make it precise, we tried not to miss any false negatives, which is missing bugs. So if you're familiar with abstract interpretation, we use that framework to make our analysis sound so that we don't miss any bugs. So that's why we have we capture the true bugs, but we also have a bunch of false alarms altogether. So that's why there are a bunch of false alarms, but only few alarms. I mean, few bugs, which is mainly investigated from ourselves or those reported CVEs, those reported bugs. That's why there are few alarms compared to the false alarms. And in addition, I think our framework is not limited to sound analysis because, false sound analysis comes with a bunch of false alarms, which is unfavorable situation for our experiments, which is finding true bugs among a bunch of false alarms. So I think, the framework doesn't depend on the type, whether it's sound or complete. Yeah, it's generally applicable. Thank you.
Okay, great. I'm going to jump down to the bottom and then I'm going to go back up to again. So I'm going to jump to Matthew's question that is addressed to Ryan.
Yes, I thought it was super interesting, and I was wondering when you did these experimentations if you found that most of the time the features that you identify naturally map with the organization of the code, or either in files or broader level folders, or if it's more fine-grained or kind of a different partition of the code.
Yeah, that's a good question. So it really depended on the code base, and you could argue that some of these heuristics, they would capture these features, and based on like how mature the code base is or how well maintained, like, I mean, open source software, if it's maintained by a much bigger team, they tend to organize better. So you might see some kind of hierarchical structure develop, like all the UI features might be within one compartment or one set of folders, right? But what we actually saw more often than not, even in some relatively mature software, was that something like a feature like WebSockets, for instance, which is only going to be used in the when you're dealing with like a UI and a broker compilation for Mosquitto, that one had its implementation artifacts strewn throughout the program, kind of like everywhere. So it wasn't in any one given file or folder. So a lot of times, like, you would almost never be pointed to this feature is completely implemented in this one file, because like a lot of things tend to use utility functions and things of the sort, right? So sometimes that utility function is only for that one feature. So we may end up removing one function from a utility file and then functions from a few different files that pertain just to WebSockets. So it's pretty fine granularity in terms of that. On the other side of that, you might end up in cases where it's overly coarse, where you might have something like ePull support in Mosquitto, for instance, right? But ePull is already built into the system. So that might be just, if I'm using this feature, I have a little bit of kind of boilerplate template code that interacts with it, but really the bulk of that implementation is actually in system files. So that's out of scope for us. So for something that's a relatively major feature like that, you might be only removing like tens of lines of code as opposed to thousands.
Yeah. Thanks.
Okay, great. Thank you. So now, Fuchen, you have a question for Akshay.
Oh, yes, thank you. My question is here, what is the cost of applying your method to a new language, as you said in your experiment only on Java bytecode. So what is the cost to adapting this method to a new language such as C++ and some other object-oriented languages?
Right, that's a great question. And I think the technique as we present it can be applied as is to any other object-oriented language, but it remains to be seen as to how effective it is. So in Java, especially, the standard library is really large, and because of the way the Java ecosystem currently is, even the third-party libraries are really bloated. So it's really effective for Java, but it would be an interesting future work to see as to how effective this could be for C++. But the adaptation would be it would work as is for C++ as well.
Okay, thank you.
Great. Thank you. Okay, I'm going to jump to a question for Tundat because I want to make sure everybody has a question. So Tundat, I noticed in the first of all, your paper is a different paper from the others because it's a new ideas and emerging results paper. So it's a little bit more kind of, at risk and kind of innovative in terms of trying something that you haven't quite been able to validate yet. And I saw in the end of your paper, you said that it could be that designing algorithms directly to solve GNN would give more benefits in the long run. But that because it's a near paper, you think this is worth kind of exploring. And I was wondering if you can kind of tell us a little bit more about that.
Yes. So let me just repeat the question a little bit. So your point is like whether like the idea of developing a verification tool capable to solve that of JNN would be worthwhile, right? Right.
Yes, compared to a more traditional approach, because that was kind of how you ended your paper, kind of thinking about that.
Yes, thank you. I also think this is a very good question. The reason why the JNN can't be verified with existing tool is because of the JNN incorporates something called the message passing procedure instead of the normal feed-forward. This message passing procedure, in turn, have a quadratic operation in it with respect to the either the node degree or the feature. So this quadratic operation is the reason why the JNN cannot be verified with existing verification tool, which mainly consists of support linear operation. And this quadratic operation also exists in a number of other architectures, such as transformer, attention, for example. So since most of these architectures are pretty useful and widely used, I think it's worthwhile to develop such tool. Thank you.
Okay, great. And we'll just do a follow-up with Hyun Soo. He has a question for you as well.
So how does your approach may align with analyzing of GNNs? So not even considering the attacks, adversarial attacks to mess up with your GNN. In modern days, the graph, for example, SNS, friend relationships, and Reddit posts are rapidly changing day after day. So
yes. Yes, I understand. So your question is like, how can this approach be applied in the context of like maybe robustness verifications or robustness defense, right? So adversarial attack consists of like a slight change in the graph, a slight perturbation in the graph that lead to the change in this prediction. In this way, if maybe our work, the work JNN infer can be used to see to check if there exists a property that reflect or verify that the JNN work well within a predefined input space, a region in input space. So if we specified the robustness bound as a region in the input space, and it desired behavior or desired output of the JNN, and we can use the JNN infer to check if it is capable of inferring this region or this behavior as one of its output. I think it's one of the applications in this context.
Okay, great. Thank you. I think we have just time for our 2 last questions. So, Francois, did you have your question for Akshay?
Yeah, I actually read the question.
Okay.
Yeah, I didn't mention this in the talk, but the amount of reduction is sort of tunable for the user. So the user can specify what part of the library, what percentage of the library they want to analyze, and it'll accordingly tune off that much speed up for so much lost recall. So for example, if the user specifies that for a cast check analysis, they want to analyze only 3% of the partial library, they get on average 92% recall and like a 24x speed up. And those numbers will vary based on the analysis.
Okay, great. And we have one last question, which was from Matthew to Ryan. If you've already read it, Ryan, you can go for it. If you want Matthew to ask it. Matthew, you better ask.
That's the one that we already, for that one.
Oh, we did. Right? Okay. Okay. In that case, I think we've looked at all the questions. And so we have 4 minutes. So I'm going to everybody gets 30 seconds to give a kind of closing pithy statement about something super cool about what you've done, what you're going to do next, or something like that. So we'll go around. Fu Chen, you're first. I know one person had to leave early, and I can't remember who it was. It's not Fu Chen, he's here. So
Thank
30
you.
seconds.
Okay. So for a conclusion, our tool can detect the inter-contract vulnerabilities, which the priori work did not consider. And our future work will mainly focus on, like I just said before, we will focus on support more types of vulnerabilities, and we will try to detect more bugs in the real world smart contracts, and that's all. Okay.
Great, thank you. Okay, remember 30 seconds. Ryan, you're on.
Sure. For our next thing, we were looking at different reasons to target given features in code, and one of the things we looked at was building a framework for synthesizing functionally equivalent yet syntactically dissimilar code to replace them with. So instead of just deleting, we're actually swapping, and that would introduce some form of like a moving target defense for program diversification.
Okay,
so that's
great.
ongoing and pretty exciting.
Okay, pretty exciting stuff. How about Tandat? Are you here? Yep, 30 seconds.
Okay, so I think since our paper is new idea, I think the first thing to do is like implement it, of course, and maybe try applying in the context that maybe as Winshu mentioned, the context of robustness verification and stuff like that. Thank you.
Okay, great. Pei Ming.
I'm graduating, so I don't know what my resume for with these lines of research. But if you're asking about my future plan, I'm going to work on some project related to MLIR. If you are in anymore, also, yeah. But unfortunately, I don't know.
Great. Thank you, Hyun Soo.
So one of the possible future work would be try to integrate semantic properties to the network that would align with program analysis that is being used. And although we didn't mention it in the talk, but the base rules start from the human written rules. And one other interesting research would be making it fully data-driven.
Okay, great. Thank you. And finally, last but not least, Akshay, if you're still here. he may have had to go. I know a couple of people had to go to other sessions. Okay, let's just give a great round of applause to our speakers that are still here. Thank you very much. This was a great session. Everybody had some good questions to ask, and thank you to everybody for